Hi everyone, welcome back. Today we're going to finish up our discussion on doping. We're going to talk about non-uniform doping in semiconductors. We're going to talk a little bit about carrier transport, and we're going to do a really cool example of non-uniform doping in a semiconductor and show some really cool new properties that non-linear doped semiconductors have non-uniform doped semiconductors have that uniform doped semiconductors don't have. And but before we get started on that, I want to derive a new expression for electron and hole concentration in a semiconductor. In some cases, you're not going to have, when you're calculating these values of N and P, or you're calculating E of F or Fermi energy, you're not going to have the values of NC or NV or the conduction band or valence band energy. You may not even know what kind of semiconductor you have. And maybe you can measure it and just find out your intrinsic amount of intrinsic carriers, but you still don't know what the actual materials is. Well, let's start with what we know here. We know, and I'm just going to do it for N. Let's switch to black here. We know that N is equal to NCE to the EF minus EC over KT. And we know that Ni, our intrinsic electron concentration, is NCE to the EI minus EC over KT, right? Where for intrinsic semiconductor, EF is EI, right? And similarly, we can rewrite NC by bringing this term over here, and we can say that NC is equal to NIE. I'm just switching these terms around. When I bring it over here, I make it negative. EC minus EI over KT, just like that, right? Now what I'm going to do is I'm going to substitute this NC term here into this NC here, and then we're going to further simplify, right? So now my new N is equal to NC, which is NIE, to the EC minus EI over KT times this term here, E to the EF minus EC over KT. So now what I'm going to do is I can bring these two exponentials together, right? And then this sum together in one exponential, and I see my EC's cancel out, and I just have N is equal to NIE to the EF minus EI over KT. And that is a new term that we now have for the number of electrons in a semiconductor. Similarly, we can do the same thing for the number of holes, starting with this equation up here and going through the same process. Using this, setting P to PI, which is just Ni, right? And changing EF to EI, and then solving for NV, and then plugging it back into that equation and solving for this. And then what we find is P is equal to NIE to the EI minus EF over KT, right? And if you look at that in terms of your energy bands, we got conduction band, valence band. Let's say if it's N-type, your Fermi level, this is EI, right? Intrinsic Fermi level. If it's N-type, your Fermi level is somewhere above EI, right? And so N is going to be Ni times the exponential EF minus EI, which is this right here, which is a positive quantity. So this delta E is just EF minus EI, right? And so we'll see that the further the EF is from E, or the higher up it is close to the conduction band, the higher number of carriers we have. And similarly for P, we can say if it's a P-type, P-dope, a Fermi level is somewhere below EI, right? And then our new term is this minus, EI minus this. So this DE here is just this term right here. So as DE increases, this whole term increases, thus P increases. Another way to look at that is as our Fermi level gets closer and closer to the valence band, we get more and more holes, right? So I'm going to rewrite that up here using a pink marker. P is equal to N, NIE to the EI minus EF over KT. N is equal to NIE to the EF minus EI over KT. Okay, enough of the carrier statistics. Last time I derived the Poisson equation, but I feel like I did kind of a bad job. So I'm gonna rederive the Poisson equation and starting off with some of Maxwell's equations and some stuff that you should recognize from electromagnetism, or if you take applied electromagnetics, this stuff should be familiar from you. So we start with the fact that the electric field density is equal to D is equal to little e, which is your permittivity of a material. It's material specific, times your electric field. And these are vectors, of course, and they can have an x, y, and z component, or an ijk component, if you like. And then we start with the differential form of Gauss's law, which is this, is equal to rho over e. Where rho, again, is our charge density, and we know that to be, well, I'm rewriting Q as just E, where E is 1.6 times 10 to the negative 19 coulombs, right? It's P minus N plus N plus D minus N minus. So basically, it's the sum of all your positive charges, right? And we subtract our positive charges from our negative charges, and that's rho, right? And we also know that del of V, the potential, is equal to del, it's just equal to negative electric field, right? Just like that, right? And I'm just going to rewrite this. This could be, negative EXI plus EY J hat plus EZ K hat, right? Just like that, right? So now what we do is we're going to combine these together, right? Because what if I have del of V? Well, del of V is just negative E. So we have a del negative E. And what's del negative E? Well, that's this guy right here, differential form of Gauss's law, which is equal to, I can bring this negative sign out, negative rho over E, right? And I can rewrite this as d squared over dx squared V plus d squared over dy squared V plus d squared over dz squared V is equal to negative d over dx of E x minus del over del y L y minus del over del z is y, right? Just like that is equal to this term over here, right? But what if we just are concerned with one dimension, right? That's really all we're going to be dealing with is just one-dimensional semiconductors for now. Just to derive these general expressions. To get a at least decent idea of what's going on here. If we just in terms of x, well then I can rewrite this as d squared of V over dx squared is equal to negative d E over dx, right? Which is equal to negative rho over epsilon. Just like that. And this is our one-dimensional Poisson equation. It's like the Laplace equation. If you've taken any partial differential equations, the Laplace equation, basically, which is del squared equals 0. But in this case, del squared is not equal to 0. You know, it's not homogeneous. So we have some other functions over here. So I'm going to rewrite that over here. This is before. The Poisson equation. Except I'm going to write V. I'm going to write it in terms of just general potential, which is just V. And that is our Poisson equation. And we're going to show some applications in that a little bit later on. But you can tell, just by looking at it, that you know how potential, electric field, and charge concentration are all related to each other. They're all nearly 20. You know, so if we do have something with a non-uniform doping concentration, that's going to affect our charge. So this all of a sudden becomes a function, right? So the second derivative of our potential is now, let's say, you know, it's constant. It's non-zero, right? So that's something we can look at. Like if potential, if your doping is an exponential function, you know, it's like a e to the nx. You know, it's increasing exponentially. Well, every time you differentiate or integrate, you know, an exponential, it's just some term times an exponential. You know what I mean? So you can never make it go to 0. You know, so in that case, you definitely are going to have a non-zero potential if you have exponential doping. Okay, so now we're going to talk about a little bit more about doping concentrations and non-uniform doping, right? So we've got X, right? And you know, this is a semiconductor, right, from 0 to some distance out, right? And let's say doping increases like this, right? Just like that. And this would be, you know, ND naught, right? And this would be NDL, and it has some equation, you know, ND equals to MX plus ND naught, right? That should make sense. Draw that up a little. ND of X equals MX plus ND naught, right? Okay, so now doping is a function of X. It varies over time, so there's a doping gradient. Furthermore, yeah, has some linear equation of that. So that means that we're going to assume 100% ionization. So what happens is all of our donor ions are going to build up over here. So at this point right here, we're going to have, because donor ions are fixed, you know, they're in the lattice, they're not going anywhere, right? They're stuck in the lattice by these covalent bonds, right? And you know, and what's happening is as we go from 0 to L, our ionized donor concentration increases. Well, each one of these donors is giving up an electron, and it's going, you know, up to the conduction band. But because of you know, electrons follow, you know, electrons in a non-degenerate semiconductor follow Fick's law, you know, which is you know, d sub n over dt of x is equal to negative d sub n d del sub n over dx, right? Or in a more simple term, they go from an area of high concentration to low concentration. So what happens is electrons will diffuse left just like this, right? Just like that, right? And then all of a sudden you get this, you get all these negative charges right here. And what happens with that, you've got to build up the negative charges over here and build up the positive charges over here. You get an electric field in this direction, right? A built-in electric field, right? So this is a characteristic you will not see with uniformly doped semiconductors. With uniformly doped semiconductors, there will be no electric field. E will be 0 anywhere in the semiconductor, right? So let's look at another. So you get these build up the charges over here, right? And you get all these positive charges over here, right? Which gives rise to some electric field, E. Well, electrons, remember, they move in the opposite direction of an electric field. So what are they going to do? They're the electrons that diffuse this way, they're going to drift this way. by some drift velocity Vd, right? And that Vd is equal to mu sub n times the electric field, right? So mu sub n is called the mobility, and we'll get into that in a little bit. And that's basically a number that expresses how well an electron moves through a lattice, and if you have a lot of scattering and a lot of impurities and a lot of things that can impede it from moving, then mu of n is very small. And if you have a very intrinsic lattice, a very clean lattice, I guess, very pure, then mu sub n is very high. So and we'll get into that a little later on. So we have this drift current, right, which we're going to express as and oh, by the way, remember, electrons are negatively charged, so the direction of current is always opposite the direction that the electron is traveling. So our what we call our drift current here is actually in this direction, right? Call this J drift. And our diffusion current, electrons are diffusing this way, high concentration to low concentration, is going to be in this direction here. Right? Drift current density, diffusion current density. Right? So we need an expression for both of these, right? So J drift for an electron is equal to the charge of the electron E times the number of electrons N times your Vd, which is just mu sub n E. Right? Mu sub n is a constant, E is a constant, and is how many electrons you have, right? And E could be, we do have, charges changing over distance. There is a gradient, so E may not be a constant, in this case. So similarly for diffusion, we get J diffusion for an electron is equal to charge times another constant called the diffusivity. And we'll find diffusivity is actually very much related to mobility. When we start looking at the Einstein relation a little bit, call that d sub n times your gradient dn over dx. And if we're dealing with a linear doping gradient and we're assuming 100% ionization, then dn just becomes d over dx, right? Which basically is just the slope of this nd right here, which is just n, just like that. And we can find that actually by plugging in, n dl minus n d naught over l. But we'll get to that later. So we have a drift current component and a diffusion current component. So the total amount of electron current in a semiconductor is given by the sum of the two, which is J sub n is equal to J drift plus J diffusion, which is E n mu sub n E plus E d sub n dn over dx. Just like that, right? Very important. This is the total electron current in a semiconductor, right? And similarly, if this were acceptor doped, if we had a doping gradient of acceptors going up like this, and so it's p-type, but it's varying over distance, then we're going to have a very similar equation for holes, which is Jp is equal to EP mu sub p E minus, the only difference here, E d sub p dp over dx, just like that. So, we just derived current density for an electron and a hole in a semiconductor. So going back to this nonlinear doping, we're going to look at an actual example problem where this would be used, right? So I'm actually going to rewrite this. J sub n is equal to E n mu sub n E plus E, whoops, E d sub n dn over dx, right? And then J sub p is equal to E p mu sub p E plus, whoops, minus E d sub p dp over dx. And according to the Einstein relation, diffusivity and mobility are related through this, this term right here. D over mu is equal to kt over E. Right? Okay, I'm gonna erase this. Make sure you can see that through there. Okay, good. Just about. So let's go back to that same problem, right? We have doping, which is ND of x is equal to mx plus ND naught, right? Okay. And we want to find a couple things. We want to find an equation for energy, right? And if we can find an equation for energy, then we can find an energy band diagram for the conduction band and the valence band and the Fermi energy, right? And just by what we know already conceptually, when we derive this, we know that it goes from the doping increases, which means our concentration increases as a function of x, right? So that means as we go further and further down, we get more electrons, right? Higher concentration. Well, what does that mean in terms of the Fermi level, right? As we showed in the very beginning, as concentration of electrons increases, the Fermi level gets closer and closer to the conduction band, right? And this isn't p-type, right? So we know that everywhere in here, right, and we assume 100% ionization, right? We're also assuming, I forgot to say that ND is greater than Ni everywhere. So basically, that's saying that assuming 100% ionization, this is an n-type semiconductor everywhere. So the Fermi level is always going to be above the intrinsic Fermi level, right? So we know that it's going to look something basically like this, right? Right. This is EC, this is EV, right? And this is EF, just like that. That's our Fermi level, right? And this could be EI, right? So how do we prove that mathematically, right? Well, remember last time, we don't really know the exact value of the conduction band and the valence band energies, right? These are for electrons, right? With electrons, you can never find the exact place in energy and time or momentum where they are. We can find these delta values, these changes in them, And so what we do is we reference EV to be 0, and I'm going to reference EV to be equals 0 at this point right here, x equals to L, right? So I'm going to say EV equals 0 at x equals L, right? And this might work as a good boundary condition for some of the equations I'm about to go through, right? So, the semiconductor is like this, right? And it's doped like this, right? But it's not connected to any power source. There isn't a resistor here or a power supply or anything like that. It's not connected, right? And what do we know about current from Kirchhoff's current law? Is that in order for current to flow, the circuit must be connected, right? There has to be something connected. So eventually, what happens? Yeah, we have drift current. Yeah, we have diffusion current, but they cancel out, And they're gonna. The sum of them has to be 0, unless these are connected. So I can write J. I can assume that J of n, which is E n mu sub n E plus E d sub n dn over dx is equal to 0, right? Okay, so I'm thinking if we can find E, right, we know that from this term here, d over dx equals negative dE over dx equals d squared phi over dx squared, right? Well, in a semiconductor, in solid state physics, when you consider an electron in a crystal, the potential energy of that electron is always the negative of the kinetic energy, right? So from that, I know that that E, electric field, is just equal to 1 over Q, 1 over E, right? Or dE over dx, right? Just like that. I don't know if that makes a lot of sense, but it's electric field, you know, E is equal to negative d phi over dx, right? And E is equal to 1 over Q, you know, phi, right? So I want to make this in terms of energy, so I bring E down here, and you know, and I make it positive, and we get this term right here. So I'm going to write this right here. E is equal to 1 over E, the energy over dx. Okay. And so I know this is 0, right? So I'm going to cancel out terms. E, gone, right? So I get n mu sub n E equals negative dn over dx, right? What is dn over dx? It is just the slope of this gradient right here, m, right? So I rewrite this E is equal, oh, and by the way, 100% ionization. 100% ionization means n d is equal to n, or n d plus is equal to n d, which is equal to n, right? So I solve for that. That's negative d sub n over n mu sub n dn over dx, right? Oh, by the way, that's just, what is dn over dx? It's just m. It's just the slope of that, right? And by the way, mu sub n and d sub n, I can simplify that, right? That's, oh, by the way, this is n d of x, right? Let me just rewrite this here. I'm simplifying too fast maybe. So negative d sub n over n mu sub n dn over dx. Well, dn over dx is just equal to the slope of this of our doping, right? Which is just m, right? And what does dn equal from the Einstein relation, right? And this is true for hole and electron, you know, hole and electron. I can say that d sub n is equal to mu sub n kt over E, right? So now I'm going to rewrite, oh, by the way, and then n is equal to nd of x, right? So E is equal to negative mu sub n's cancel out. I get kt over E times, well, this becomes m times, and then that cancels these out, right? Times 1 over n, which is just nd of x, which is just 1 over mx plus nd naught, right? Just some general equation. You know, I don't want to plug in any numbers yet because it's better to figure this stuff out and then, you know, write a program for it and plug it in the computer and really see what the relationships are, you know, instead of just plugging in numbers all the time, right? Okay, so I have an expression for electric field, right, in this semiconductor. And so now I want to find the potential across it, right? Or I'm sorry, I want to find the energy, right? And I have this expression right here, right? So, well, I bring this over here. I'm saying E of E equals dE over dx.